In this video, we will continue to talk about how to define data in assembly language under the .dat directive. So the first thing that's introduced, one operator we call dup. So the dup represents for duplicate. So use the dup, you can duplicate one data you specify multiple times. So that kind of is allocated the space for an array or a string. So the syntax for the dup is like here. You have your dup operator. Before that will be a number. We call that counter. That means how many times you want to duplicate. So the value you want to duplicate is after the parentheses, in the parentheses after the dup. So the argument here means the value you want to duplicate. So that's your counter and argument. They need to be a constant value or a constant expression. So that's we know how many value we want to duplicate and what the value to duplicate. So we see, for example, so that's a dup operator. So you want to duplicate 20, 0. So this 20, 0 will be reside in what kind of value? So that's why your dup operator usually is after your data label and your size. So the dup actually is in the initial value you want to assign. So for example, now I have the val 1 byte. So then I have 20 dup 0. So I have 20, 0 to fill up. So after the val 1, I have 20, 0 in byte. So sometimes the same thing, you can using the dup, but you don't specify the value. But here the good thing is we know we want to allocate 20 byte. Don't initial the value. So then that will be after the val 2. So your dup also can specify a string. So then you have 4 string. So 4 stack we will repeat. So that's after the val 3. So then you also can have your val 4. You can combine the value and the dup operator. So this one means I start from val 4. Each element size is byte. Let's have one value 10 first. Then you see comma. So then you can have a dup operator. I will have 3, 0 followed by the 10. Then I have 20. So that's why total is 5 byte. So we can see one by one. I just show you for this in the memory address how they look like. So that's earlier we say, right? You see in the memory address, you see total you have 5 byte. Okay, so here we have 5. So then we call that the val 4. So we make the val 4 at the beginning for. So that's the location val 4 point to the beginning for the location. So that's why I see you have 110. Then you have 3, 0. So just followed by 3, 0. Okay, so then you have 20. So from now on, anytime when you have your data defined, please make sure you know how in memory location, how they look like. So that's why we see total you have 5 byte. So then you can think about how the val 1, val 2 will look like. But you see when they occupy the memory address, they occupy in the memory, they will do one by one. So we have val 1 first, then we have val 2, then you have val 3. So here you will see you have 4 times stack. So that's why they just stack, stack, stack. They do 4 times. So that's the dup operator. So you can see the dup operator will be in the value you want to assign. So dup operator, of course, because you repeat a value, they will create array or string. So the previous video, we show you how to create the byte array. So now here is, you can actually define word array as well. So we see the example how we define word. or you want to have assigned 2-byte data. So no matter word or S word, they will define storage for 16-bit integer. So then they can be single value or multiple value. So 16-bit is 2-byte. So or you can say that 2-byte is 2 character. So this one, words 1, that's a data label, then 2-byte, then value. So data label, 2-byte, then sign value. Of course, you can define data value size, but without overwrite the value. They're just using the previously what the memory location have the value. So each one actually they just do 1 by 1, and also since they after the words they only specify one value, so that's kind of is a single variable location. So before the legacy, we're using the D word. DW represent for that. So that actually send they are 2-byte. So words actually, right, you can also make the array. So how you will do is, you see I have my list. Each one is 2-byte words. So then I have 1, 2, 3, 4, 5. So that's why you see that's the array of the word they look like here. So then your offset, of course, they do 2-byte each one. That's why you can see here your label my list will be beginning of the array. So then you have each one is 2-byte. So that's why each occupied data will be residing 2-byte. So then we have value 1, 2, 3, 4, 5. So that's how they look like in the array. So when you define the array, actually you just have one data label. Then how many memory for each element? You just need to continue to assign the value. Of course, the array can be byte, can be word, or can be D word. So that's why here you can see continue with the D word. You just have the 4 bytes for each element. They can be D word unsigned or SD word for the sign. So the D word, of course, you still can using the DOP. So that's why you can see in val 3, they are declaring an array. So each array element is the word 4 byte. So I want to do 20 of that. I don't reassign any value. So then you can see here in this instruction, this statement they make 20 times 4, they have 80 bytes. Of course, you can continue just 1 by 1. So that's the D word array. So sometimes when we define one data label, we assign the size is multiple bytes. So for example, you see this one is 4 bytes. But like we say, in memory, they still count byte by byte. So even we assign 4 bytes for the whole number like this, 1, 2, 3, 4, 5, 6, 7 in hexadecimal. But then how they really look like, the value resides in that 4 byte. So in assembly language, you want to talk about the little endian. So even we define the val 1 is D words, 1, 2, 3, 4, 5, 6, 7, 8. Right, before I can show you just like you only have one whole element. Okay, you can consider that's one whole element, one piece. Then you say that's 4 bytes. So that's why you just have 1, 2, 3, 4, 5, 6, 7, 8 H. But that's we say they are the whole thing is 4 bytes. But like we say in memory address, they all have byte by byte. So just this one piece is 4 bytes. So then if we see just byte by byte, how they look like. So all the data actually in assembly language longer than 1 byte, they store their individual bytes in reverse order. The least significant byte occurred at the first, the lowest memory address. So that's why we see here, that's the whole piece, right? But when we have this whole piece in 4 bytes, C in byte by byte. So beginning here is your val 1. That's how they look like. You have 4 bytes. But when this 4 byte, we see byte by byte. In assembly language, we use the little endian order. So you see here, val 1 still point to the beginning for the memory. So then how they occupy this 4 bytes? That's we say the least significant byte occurred at first. So that's why this last one close to the val, they will occupy first. Then we do the next one, next one, next one. So this way we call the little endian order. So little endian order is how if we have the data type is greater than 1 byte. So how we store the individual byte in the reverse order. So when we say reverse order, actually it's not really reverse. They just start from the least significant byte occur at first. So on the other hand, let me continue to show you this little endian, how they look like. So this one earlier we talked about how to define data. So that's the sample example in the assembling code. So you still have your directive for the 32-bit. So then you have data. Then you see data segment, you just start data. If you need to use those variables for your code, you need to define .data first. So after you define .data, so you see here you have .code directive. So that's your main procedure. So you see that we show you on Tuesday. You define one data label. The size is 4 byte D word. So when you give them 2000, 2000, it has decimal. What happened is in your memory address, the first val occupied the beginning of the location. So then we have 4 bytes. But these 4 bytes, if you see byte by byte, they will use the least significant one at the beginning. So they do like 20002000 like that. Kind of you read from this way, but in memory address, they do from the back to the most significant one. So of course, continue, you will have the second val. So you see they occupy another 4 bytes. But you see, because they are all 1, you won't see the difference. So then you have third val. They have another 4 bytes. That's order 2. So that's the little endian, how we store the data in assembly language. In assembly language, also we can assign symbolic constant. So those constants, the same thing, we will declare that's under the .data block. So you create an identifier with the integer expression. So the symbol do not using the reserved storage. They just have using the constant number to refer to that location. So when you have a constant number to assign, you just see, for example, I have a count equal to 500. So then you can just using this way. So this way they were using the count variable to store the value for 500. So actually it's no really have the memory address for this one. So that's the constant number you can assign. Now we have a couple of different ways to assign the constant value or a constant string. So here actually I just want you to do the self-reading for the following slides because that actually is just very lectury. So at the end, for the last topic I want to finish in this video is we want to see how to calculate the size of a byte array. For this one, actually, we will introduce one operator. So this operator we call the current location counter. We have the $sign operator, but this $sign operator actually will return you the current memory location address. So for example, you see here, the following declare a variable we call self-PTR. So this self-PTR, we just define the size is D word. Because this PTR we want to using to store the current memory address. In 32-bit environment, the memory address will be in 4 bytes. So that's why you have this self-PTR data label. So the size is 4 bytes. But here you see you give them the $sign. So this $sign actually give you the current variable of set value. So that's just a location for that. So that's why you will see that's the current location in the memory address, right? We told you where it is. But afterward, if you define a list array called byte 10, 20, 30, 40. So then you can using the $ minus beginning. That's your